we started force analysis, and an example of where you would use something like that is, say, you have say something huge like this industrial oven, okay, and you have the door of this being operated by a linkage. So you have something huge like this. Obviously the links also will have significant mass. So in many cases, so something like this, it's not the high speeds that you're worried about, but it would be more of a quasi-static analysis. But you would need to find out. So for instance, if it was in the halfway open position, what would be the torque that I would require in order to hold it open in that position? Okay, so that may be something. So this is sort of an example of where you would do the force analysis. So this is a 4-bar linkage. So here, even though the individual links may not have accelerations, it's just the weight itself can be a significant force that needs to be balanced, and so the input torque would in essence be trying to balance the so in any particular position of the linkage you would be looking at balancing this configuration. Okay, so you would do the force analysis like we did last time, do the individual free setup. Again, you'll have 9 equations, 9 unknowns, and using that you would find, say, at different configurations what would be the torque required. Now from a safety issue, something like this, okay, say there is a motor that's operating the opening and closing, and say it fails, or there's a power cut and there's no backup, right? This can be quite a dangerous thing, right? The weight itself is so significant that, so ideally you would want this mechanism to just stay in that place. So if the power goes off, you want the mechanism, which is possible. So if I had a mechanism on a horizontal plane, I move it to a certain position, it's going to stay there, right? On its own, it's not going to move to another. But in many cases in real life, we are operating under the effect of gravity. Many mechanisms will be vertical and will be under the influence of gravity. So in a case like this, you want to be able to ensure safety, and also you want to be able to operate it, even the motor. So you want to be able to optimize it. You don't want a really high torque motor perhaps to do this, or if you want to operate it manually, then that's when we start looking at what we call balancing. Okay, so in balancing, essentially what we try to do is, you try to, as the mechanism moves, right, you have these moving members, so the overall CG of the mechanism keeps moving. Okay, because of, if you can somehow make that the CG of the mechanism stay stationary, okay, then, so the potential energy remains constant, then at every position it's going to be in equilibrium. So to move it from one position to another is going to take, theoretically it will take 0 effort, but practically it will take only a little bit of effort. If it is exactly balanced, I should be able to move it from one position to another with 0 torque, essentially, because it's all it's in equilibrium at that. So this would be a case where in the new position it's in equilibrium. So it's like neutral equilibrium. So at every position it is in static equilibrium. So balancing of linkages has applications like this, where, say for safety or to reduce the effort that you want to do. I showed you the example of the standing wheelchair, right? You're reducing the effort of, you have the weight of the person always acting. So you have to somehow account for that so that you can reduce the effort required to operate the mechanism. So balancing, essentially you are trying to make the potential energy constant or fairly constant, so that even if you have to apply a torque, it's sort of, there's a small variation in the torque. The effort is more or less uniform when you are operating the mechanism, because otherwise you're going to have huge variations as this mechanism moves. So balancing is also very important. In high speed mechanisms, where we were, what you have done in KDOM, for instance, the balancing, that was more for balancing the inertial forces. So that could apply even if, say, I have a mechanism that's on the horizontal plane. Okay, but I ran it at high speeds. I would still have to do balancing in order to balance the inertial forces in the mechanism. Here we are talking about static or nearly static applications, but you are balancing some constant forces, mainly gravity, which or it could be a load. So some load has to be moved up and down. So you want that to do it with minimal effort. So mainly effects of gravity can be accounted for by using balancing. So this balancing can be done using counterweights, or it can be done using springs. And I'll just show you a couple of examples of both cases, and you will have the opportunity to apply that for your project. Okay, so this is basically 3 moving links. Let's just start off with a single link. So if you want to balance a single link that is moving about a fixed pivot is generally called a rotor. So its motion will just be pure rotation about the pivot. So let's just say we have a link that has, say, it's like a bell crank. So it's, say, shaped like this, and each arm, I can say it has, the CG is located like this. So I have an M1 and an M2, okay, mass of this, and let's say this is defined by the vector R1, this is defined by the vector R2, theta 1, so I have, in this case, M1G acting like this, M2G acting in this manner. So if I have a link like this, right, in the vertical plane, subject to the influence of gravity, then it's not, if I just leave it, okay, because of the two limbs have different masses, it may, for some value of theta, it may be that it is balanced, it doesn't move from that position, but in most cases it's not going to be the case. Okay, if I leave it, it's going to move on its own. So that's when we say it's not balanced. So you have a clockwise torque which is equal to M1 G r1 cos theta 1, and I have a counterclockwise torque on the sling equal to m2g r2 cos theta 2. Okay, this is due to gravity. So at some position these two may be equal, but really at most positions they're not going to be equal, right? In general it will, so that we call this a state of, so in may be equal. In others we say it is in a state of static imbalance or unbalance. So we define an unbalanced vector. We define a vector. So capital letters, remember, are vectors. U equal to M, U1 equal to M R1, M1 R1, and U2 equal to M2 R2. Okay, so the total unbalance in the system like this is U1 plus U2 and if I define it in terms of the CG, this would be M1 plus M2 into some R0, where this is the position vector of the CG of the system. So if I want it to be balanced, for static balance, right, I want it to be, I need to compensate the unbalance by another balancing vector. So I say the total compensated UB such that UB plus U0 should be equal to 0. That is UB plus sigma mi ri equal to 0. So if I say this is the total, so this whole thing, if I have, after balancing, I have all this mass located at some empty RT, okay, that should be this should be 0. Mass can't be 0, total mass can't be 0, which means this has to be located, that means the total CG of the balance system has to be located at the pivot. If the total CG of the balance system is located at the pivot, then there is no torque due to gravity. Okay? And it doesn't matter how you position the rotor, it's going to stay there, because the total CG of the system does not change. Okay, so this implies RT is equal to 0, implies the total CG, this is after balancing. So you add or subtract a mass at some distance in such a way that this becomes 0. Okay, the total CG after balancing lies at the pivot. So no matter how the rotor rotates, the CG will not move. So this is the basic principle of balancing. We did this even when we did the balancing. So the balancing mass can be added or removed from the rotor. So negative mass means you are removing mass from the rotor. Balancing mass can be usually if you are running the rotor at a constant angular velocity, you use the same thing, because there again you have m I r I omega square. The inertial forces is, that's the changing forces, that's what you want to balance. So you would similarly have this plus some balancing mass RB omega square is equal to 0. You would do the same thing when the rotor. Here of course we are looking at gravity balancing. We are not looking at the inertial forces, but this is what you would have done in your K down, right? We did the, and then dynamic balancing is when you are also looking at another plane. You are also looking at the so this is, you are looking at this one plane where you are adding this mass, but if you look at the bearings, so this will reduce the force on the net shaking force. You will be able to reduce to 0 when you do this. But if they are separated, so axially if you have a length, then you have to do dynamic balancing, where you look at that plane and then you have to balance the moments also in that plane. We are going to look at planar. We've been looking at planar mechanisms, and we are looking at static balancing of mechanisms. Okay, so that is so now let's look at the same. I told you about this problem with this door, right? So if I want to balance this, okay, I want to balance this mechanism so that no matter where it is, it will stay in that position. Okay, so in order to be able to do that, let's look at, because balancing a rotor is fairly easy. Okay, you can just add counterweight like this and balance that. In the case of, so if you look at a 4 bar, you have two links which are rotors, link 2 and link 4. Link 2 and link 4 are moving around fixed pivots. So I could separate those two and kind of balance them as rotors, so that the CG of that comes to this. But the tricky part is this, the coupler. The coupler, because it has complex motion in the plane, how are you going to, as the mechanism moves, how are you going to keep the CG of that constant in the plane? Okay, so that's what we are going to look at now. So for the oven door, I'll give that to you as a problem that you can solve, the force analysis that you can do. Now let's look at the say for the same application, we want to do the static balancing of a 4 bar linkage. So let's say this coupler, its CG is located here. It has a mass m3. So I have Z2 equal to R2 e power I theta 2. We call this ZC. This is Z3. And Z2. Usual notation. And this, the location of the center of mass of length 3 is at a specific, so this phi would be constant because this is one rigid body, right? So link 2 and link 4 can be balanced as rotors. So let's not worry about that here. Okay, so they can be balanced as rotors. So you can bring their CG easily to that particular pivot. The motion of the coupler is what we are interested in. Let's say this is located R3 gives the location of the center of mass of the coupler. So what I am interested in balancing is this unbalanced vector U3 equal to M3 R3. Okay. So R3, I can write it as Z2 plus ZC. So I can write U3 as M3 into Z2 plus ZC. I can write the unit vector along this. Okay, I can write this as M3 into Z2 plus RC into Z3 by R3, okay, into e power I5. Can I do that? Okay, this is Z3 by R3 is the unit vector along. So that's equal to e power I theta 3. Okay, so I'm just, because this is RC e power I of theta 3 plus 5. Right, that I am writing like this. Because e power I theta 3, I can write it as Z3 by R3. Okay. From the loop closure for the 4 bar, I have here Z2 plus Z3 equal to Z1 plus Z4. Therefore, I can write Z3 in terms of the other vectors as Z1 plus Z4 minus Z2. I can substitute that back into the unbalanced vector as u3 equal to m3 into z2 plus rc by r3 e power i5 into minus z2 plus z1 plus z4. Okay, I've only substituted for R3 in terms of the other vectors. So I can now write this as M3 Z2 into 1 minus RC by R3 e power i5 plus M3 Z1 RC by R3 e power i5 plus M3 Z4 RC by R3 e power i5, and then let me add and subtract M3 Z1 from this equation, adding and subtracting. So this one now, if I group, I get M3 into Z2 1 minus RC by R3 e power i5 plus M3 into Z1 plus Z4 RC by R3. You will see why I added and subtracted e power i5, okay, plus M3 Z1 into RC by R3 e power i5 minus 1. Now look at this. Z2 is the vector here, right? So this is like an unbalanced vector that is attached to, that is affected by the movement of Z2. Okay, because as Z2 changes, this unbalanced vector will change. Look at this one, Z1. So my loop closure is, okay, my loop closure is here. So if I look at this one, this is something that varies with Z2 because everything else is constant here. Phi is constant, RC, R3 are lengths, everything else is constant. So this is equivalent to, it's like an unbalanced vector that is attached to link 2. Okay, of mass, that is mass M3 attached to link 2 in some fashion, which moves with link 2, which changes with link 2. Okay, so this is equivalent to mass M3 link 2. Look at this one, Z1 plus Z4 something. Okay, so Z4 is the varying quantity here, everything else does not change. Z1 is your fixed link, does not change. So this is equivalent to a mass M3 attached to link 4. Okay, look at this one. This is a constant term, does not change as the mechanism moves. So yes, it is an unbalanced vector, but it's not changing. It's constant. So it's just something you have to live with. But it's not something that's going to. It's the unbalance of a non-moving mass. Okay, it's a non-moving mass. So what it essentially means is it will not affect the CG of the system because it does not move. The CG of the system will not change. The CG will not be at a pivot like in the case of the other two. Okay, but it's also not going to change. So this will be something that will contribute to the CG being someplace other than at a pivot. Okay, so you have a finite. So this is the unbalance due to a non-moving mass. So I can write this, the first term, I can write this as M3 into M3 into Z2 plus R2 dash plus M3 into Z1 plus an R4 dash, okay, plus a constant term. So what is my R2 dash? It is the vector Z2, okay, minus Z2 scaled by RC by R3 and then rotated by phi. Okay, so if I want to locate it here, I can say so I locate this is R2 dash, okay, and this would be at an angle, that angle would be phi, and this mass is M3. So this is attached to link 2. So, and in this case you have Z1 plus R4 dash, where this is like this. This is the angle phi. This is R4 dash. This is M3. Okay. So the unbalance due to the coupler can be reduced. So I can replace it by an equivalent mass M3 located on link 2 like this, and on link 4, and then of course a constant term, okay, constant term that's attached to link 1. So what this tells me is now my link 2 and link 4 are simply rotors. So in addition to their mass, which is located at their CG, their total mass that I want to balance is that one plus due to this M3 located at R2 dash on link 2 and similarly on link 4. Okay, if I do that, if I balance that, then I can say that the varying component is made 0. So there is no so the unbalanced vector due to mass of coupler can be replaced by unbalanced vectors due to equivalent masses on link 2 and link 4. Link 2 and link 4 can then be balanced as rotors by including their own mass and the equivalent masses. Yes, Jay.
Could I balance the coupler about I13, treating it as a rotor?
Take a look at that. I13 is changing. That is the problem.
Sorry.
If it was a fixed point, yes, you could do that. And that is what you'll end up with the same sort of result. Okay. So by doing this, the total unbalanced vector, that is after balancing, of the linkage will not move. When the linkage moves, therefore the total, it implies that the total CG of the linkage remains constant. So you cannot make the unbalanced vector 0 for the 4 bar, but its variation can be made 0. Okay, so it remains at a constant CG. Okay, we will stop here. Tomorrow we will do static balancing using springs instead of masses. Okay, so masses, this is one way of doing the balancing. The only problem is you are increasing the mass of the entire system. You are adding mass to the system. So for instance, if you had if it is in a static place, fine, but if you had to make the pool lift portable, for instance, right, you're going to carry all the extra mass also. The balancing happens for the gravity, but other things are going to be affected by the increased mass. It also increases cost, because anytime you're using more material, you're going to increase the cost of the system as well. So those are some of the drawbacks of doing balancing with counterweights. Like here, springs offer another alternative for doing this kind of balancing. They come with their own challenges.